All right. I would have normally said Srikant needs no introducing, but given he's been introduced once, he definitely needs no more introducing. Over to you.
Okay. So the algorithm we discussed was take the Q value for that state alone using this algorithm. Okay, but as I mentioned before, so Q is a vector that is S a dimension, okay, where S is the size of the states or the state space, and the cardinality of S is the size, and the cardinality of A is the action space. Okay, so what we want to do is we want to try to approximate Q using a linear function approximation. Okay, and so here theta lives in some dimension RD, and this is what you want to learn, and this is a known feature vector. So since D is considered to be much, I mean, we choose D to be much smaller than S times A, so that learning this would be, in some sense, much easier than you just even storing it would be much easier, right? Okay, so Sutton proposed an algorithm for this problem in 1988, and Tsitsiklis and Van Roy proved that that algorithm converges in 1997 or 98, I can't remember. And using the techniques that we learned this morning, you can get finite time performance bounds. Okay, but what is most interesting, some people were asking, so what is sort of the frontier of research here? One interesting question is, I mean, of course, you don't use linear function approximation, you use a neural network to approximate it. And so in some recent work, we have extended this to neural networks, where this approximation is done using neural networks. But I'm only going to talk about the linear function approximation case here, but more generally, so you might try to approximate it as the output of a neural network with some parameter W, for example, and you try to learn the parameter. Let me just call it theta here too. So I try to learn the theta. It's a nonlinear function approximation. And for those of you who know about the NTK analysis of neural networks, it's very closely related to the NTK analysis. The neural tangent kernel analysis essentially tries to linearize this and try to do something with it. And so that's basically how we can extend the Tsitsiklis-Van Roy approach to neural networks. But today, I'm just going to stick with this Cole 2019 paper and just pretend to obtain finite time bounds. Okay. So this algorithm can also be thought of as one step of gradient descent in the following sense. So minimize over Q. Okay. Sorry. So you assume that the current estimate of QK is going to be used to evaluate the function at the next state S prime A prime. And then for the current state, you pretend like I want to learn what the Q function is. So if you differentiate this, scalar, and then set Q equals QK of SA, then this is just gradient descent, right? Everybody understand this? So just as though you're doing one step of gradient descent again, changing the objective next time to QK plus 1 and doing one more step of gradient descent and so on. Seems like a silly algorithm, but remarkably it works. And this is what Tsitsiglis and Man Roy proved. Okay. And so what happens in the case of function approximation? So the natural thing to do in the case of function approximation would be use this as the objective function, right? So you have a current estimate for theta. You believe that that estimate is going to give you the value function for the next state action pair. But for the current state action pair, you're trying to learn a new theta. It's bizarre, but this is what it is. Okay, and we'll see why this converges. Okay, so if you do that, then your algorithm naturally becomes theta k plus 1 is theta k minus epsilon k. Then I differentiate this, I get theta k transpose SA minus R gamma V S prime A prime. Then because I'm differentiating with respect to theta, I'll have a phi SA. Okay. It's essentially the same algorithms here. So you're using the temporal difference. Okay, this is exactly QK minus R minus gamma times this. So this is the temporal difference. But you're updating your theta in the direction of the current feature vector. That's it. Because you're trying to find a vector theta. Before we're trying to update one coordinate, a scalar quantity. Now you're updating a vector quantity. And what this suggests is that you should move theta in the direction of the current feature vector. Okay, that's clear. So in vector form, as before, okay, first, so I'm going to define a matrix phi, which consists of the feature vectors written in row form. So each row is a feature vector. So this is SA times D matrix.
Why is the reward being multiplied by B?
I've not like this, you mean?
Yeah. The reward is being multiplied by B.
Yes, the whole thing, the temporal difference is multiplied by B. Sorry, this should be SA or SA. When I differentiate this, I would get the phi SA will come out, right?
That's one question.
Sorry?
So when you're saying this works, you converges to the best.
I'll tell you what it converges to. Yeah. I'll tell you what it converges to. Okay, so in vector form, this whole thing, I'm going to ask you to believe me on this. Okay, it's very similar to the equation we had before. Since the way I have defined the phi matrix, the feature vectors are row vectors, so this would correspond to, when you write it in matrix form, it correspond to phi transpose. Turns out.
One step of gradient descent, can we interpret exactly as the same as TD, as one step of TD, or is there an approximation of the TD out there? What is the connection between?
Sorry, say that again.
What is the connection between the TD algorithm and the one step of the gradient descent? Are they?
This is all I'm saying is that this is the TD algorithm, and the TD algorithm can be interpreted as one step.
So there's an exact mapping here.
Yeah, because if you differentiate this and set Q equals QKSA, then it is the previous value minus the gradient, right? You're moving in the direction opposite. This is exactly that.
Gradient descent for this layer.
For just this one standing, then you sort of.
So there is this bootstrapping aspect, right?
Yeah, right. There's a bootstrapping aspect. So basically, we believe that this one part of it is correct and one part of it is not correct.
Yeah.
It's kind of a vague heuristic, but it's interesting that it actually works, and why it works is not very surprising based on what we learned this morning. Okay, so the key idea, successful and right, is to I don't know if they wrote it in this particular form, but basically, if you replace these two quantities by the stationary expectations, just exactly like we did in the morning, this becomes d pi, and this is phi theta, and this is r minus gamma times p pi times phi theta. So this is just the t pi operator. So this is as though there's a deterministic system perturbed by noise. Okay. So the noise part of the analysis will be exactly like I told you this morning, as long as we figure out what to do with the deterministic part. Okay. So let's see what this I guess an answer to this question. What does this try to solve? Okay. So if you look at the deterministic part, system algorithm tries to converge this point, right? Phi d phi theta equals basically we try to set this part equal to 0. If the system converges, it will try to set phi d pi phi theta. Sorry, this should be transpose. Phi transpose d pi phi theta will be equal to phi transpose d pi of p pi of d theta. Okay. So rewrite it slightly. So this can be written as theta equals assume this matrix is invertible. If it is not invertible, then there are other tricks that one can play, but I'm going to assume it's invertible. Okay, I'm just writing in terms of this. Then if I multiply both sides by phi, okay, so this is what I call this quantity Q hat, because we're trying to estimate Q hat, Q as phi theta. So we call this, so we have a fixed point equation of this form. It looks very complicated, but actually it is not, surprisingly. Do it all, it looks like this funny form. this quantity is just nothing but if you're trying to, so does anybody recognize this? Or?
Project.
Yeah, exactly. This is the projection. Suppose you're taking q hat. Suppose you take any vector and try to project it. So, so let me call some vector b. Okay, it's not the value function, but I'm just call y. So if you want to project a vector y onto the space p, what does this mean? Basically, you're trying to solve this problem. And for the projection, I'm using the weighted two-norm.
So this whole thing is just change of basis.
Exactly. So in let me write it here. It's not quite change of basis, but it's trying to find some sort of a lower dimensional approximation to the Q function. So you can think of this as Q hat equals a projection onto this free space of E pi. We're solving this fixed point equation now. This morning, we did not have this. Only additional thing we have is now Q hat is projected. So instead of having Q hat equals T pi Q hat, we have Q hat equals projection of T pi Q hat. Okay. Now, since we know T pi is a contraction, projection composed with T pi is also a contraction because it's well known that the projection operator is non-expansive. Okay, so projection operator is non-expansive. This is contractive. So projection P T pi Q hat 1 minus projection T pi Q hat 2 and the same 2d pi norm is less than or equal to gamma times. So the rest of the proof is practically identical. I mean, of course, there's some minor changes. So both algorithms can be thought of as trying to solve a fixed point equation with limited information. Okay. So both of the fixed point equations involve a probability transition matrix, which is embedded in this T pi, and we don't know it. So all we are just doing is basically trying to solve a fixed point equation without knowing the P, but it doesn't really matter. I mean, both are fixed point equations and both are contraction mappings with the same contraction coefficient. So pretty much the same proof goes through. That's why I did the tabular case first. Any questions? So you do the same thing. So you start off with some with a quadratic Lyapunov function, try to analyze it without this, and then basically add this, and then you look at, you condition on the history up to some mixing time. Since your time k, you try to condition on k minus tau, and then a lot of it works. There are some differences, of course, because the equations are different and everything, but essentially it goes through. Yeah.
So for other more complicated parameterizations, like you mentioned neural networks,
Right.
is there a way to think of those as solving the fixed point equation?
Yes, that's
with
what
some
we did in
different
our paper, in this paper that I mentioned with Semi Chechi and Mia. What we did was essentially you argue that it solves a linearized version of the neural network approximately. Okay. And then you have to look at the error between the linearized version and the true neural network, and then an extra error term would be the ability of the neural network to approximate any function in a certain class and so on. So it just adds more and more error terms and more complication to the analysis. But the spirit of it is very similar. That's why I just thought I'd do this.
So is a way to summarize that, like you're kind of changing which space B you're projecting onto ish.
Yes, exactly.
And then
So neural networks are great because you don't need to specify the phi
right.
ahead of time. So you learn in some sense, the neural network learns the parameters phi, so that brings in some additional computation and analysis. But that's basically what it is. Yeah. That's the question. Yeah.
Is there an abstraction in that the Q function, the approximate Q function we get, is no longer attainable by the underlying port? Like it's not the value of the underlying port.
No. So the overall error in your so if you want to, that's a good question. So I think so this morning we were trying to get this type of an error, right? Now basically I'm trying to get an error of this form, theta transpose or theta minus 3 star, where phi theta star is the solution to this fixed point equation. It's not right. So if you are interested in the error between true Q pi. Okay. So this is less than or equal to 2 times right. We have characterized this. This is just simply a projection error. So you have an additional error. So depending on how expressive your feature vectors are, this error will be small. But now if you have a neural network, then they have much better expressive capabilities. And then so you can try to reduce this and sort of handcrafting the feature vectors. Neural network will learn them for you. And so, but you can try to characterize that error to using this thing called MDP analysis. Called the neural tangent kernel, but of course people say that neural tangent kernels don't completely capture the full power of neural networks. So there's a lot of, so if you're looking for open problems, so it's very interesting to figure out, what can you learn through a neural network. So we have some results using the MTK analysis, but whether you can do better than that is unclear.
So yeah, still use the part. So the norm that you're doing the projection in is still under the stationary distribution.
Well, you can get a 2 norm result by getting rid of it. Then you get a 1 over t result instead of an exponential result.
And you still use the 1 over d, or like
Yeah, you can get rid of the 1 over d made by doing 1 over t.
I see.
So 1 over t convergence instead of exponential convergence. Yeah.
Like, can I think of this as that in the limit gamma goes to 1, this is the natural norm to look at, or
In the limit as gamma goes to 1.
because then we
Yeah, I think so. I think it's natural because I think the error will have 1 over 1 minus gamma. And then to get average cost results, you'll have to multiply by 1 minus gamma. So I think that'll get absorbed.
on this.
Right. Yeah.
Is there a geometric way of thinking about the projection of the neural network? Like here you're saying I have a fixed hyperplane and then just project it.
Right. So the neural network, so a neural network can be thought of as a single hidden layer neural network can be thought of as X for state and action together here. This would be a single hidden layer neural network where the neurons are represented by sigma, and the input is W. So you pass it through n neurons after doing some linear, by passing it through a weight W, and then take a linear combination. So what you try to do, I mean, very vaguely, is you try to, you hope that your initialization for the neural network is not changed very much by neural network training. Again, you have to prove all of this. And then what you try to do is you try to so this will be the linear approximation to it. So what we try to show is that actually, so you try to get a projection onto this linear approximation, and then you try to characterize whether there's an error between this linear approximation and what the neural network actually represents. And these two become small if the number of neurons become large. This is the NPK theory. How quickly, so that there the name of the game is how many neurons that you require, and all that has to be figured out. So there's a sample complexity aspect to it, and also a space complexity aspect to it in terms of the number of neurons that you require.
This is a single layer neural network, or like.
So this is, we've only been able to do it, I mean, you can do it from multiple layer neural networks, do the same analysis, but nobody has been able to show why depth is useful. Okay, so you can do all the analysis from multiple layer neural networks, but the open problem is to figure out why does adding more layers help. In representation theory, there is results that say that from representing a function point of view, the number of neurons that you require is much smaller if you use multiple layers. But from a learning perspective, why does it, how well you can approximate a function through gradient descent or something like that is still unknown. But essentially, what I'm saying is that when we do it for a neural network, we try to linearize the neural network and try to show it in that linear space to get an approximation, but then try to characterize the difference between the linear approximation to the neural network and the original neural network. So you have to characterize all of these error terms to get the final answer. Okay. Any other questions? Okay. So now I'll try to move on to how to use these principles to actually find the optimal policy. So far we've looked at TD learning, which means that you're trying to fix a policy and trying to learn the value function or the Q function associated with the policy. The Q function is also a value function, which is called state action value function. Now I'm going to talk about how to find the optimal policy. But even here, some of you were asking me over lunch, what are some interesting open issues? One non-obvious thing still is, what happens with the neural network, especially with multiple layers. So lots of work on trying to approximate neural networks using this thing called the neural tangent kernel. I really find the work, my colleague Matus Telgarsky, G and Telgarsky did a very nice analysis, which is what we sort of used embedded with. So this is just trying to understand what is called neural tangent kernel regime. And then what we did was basically took this and incorporated within reinforcement learning. So they did it primarily for classification problems. Whereas what we have in the context of reinforcement learning is a regression problem. We're trying to approximate a function by this phi theta. It's not in the ANT, we're not looking for trying to find whether an image is a cat or a dog. So it's not, the output is not a binary label. So you have to adapt this work for regression problems, and that's great. And then also incorporate it along with these T-pi recursions and so on. So we just basically work with so this paper is sort of a combination of this Code 2019 paper with Lei Ying and G. Telgarsky work, extending everything to neural networks. But single layer neural networks are, work for multiple layers, but as I said, doesn't show the power of multiple neural networks. Okay, so to find the optimal policy, of course, you have to try solve this fixed point equation, no longer pi, but the optimal Bellman operator, which has a max in it, right? So the algorithm then is somewhat repetitive, so I won't spend too much time. Thanks. So you put a max in. You don't take the next action actually that you observe in your trace, but you actually take the optimal action based on the current Q function. We should use, we call it A tilde since okay. So here I need SK, AK, and SK plus 1. I don't use AK plus 1, I do a maximization here. Okay. So this, by now the familiar technique that we've been following, can be written as so again, if you're able to analyze the deterministic system, you can analyze the stochastic system. But now there's a problem. There's a real problem here because this T is an infinity norm contraction, and it is not a d pi norm contraction, as I said before. So it's no longer compatible with the quadratic Lyapunov function that I mentioned before. Okay, so that is the problem here. So I haven't seen this proof that I'm going to mention now written anywhere. So I'm teaching this class and I'm going to make it part of my notes, but I don't think it's worth publishing. We knew this result when we wrote the 2019 paper, but it sort of seemed like a straightforward extension of that, so we never published it. But I'll tell you how exactly this
Wait, what is pi?
you start with some, so let's say you fix a policy as before, and you're just observing a trace from that. I don't need to know the optimal policy. Give me any policy that visits all state action pairs. Okay, and then yeah. So this is the idea here. Okay. So T, as Wayne mentioned, is an infinity norm contraction. It is not a contraction, as far as I know, anybody knows, in any other norm. Okay, so this is not compatible with what we did earlier. So what do I do? What is interesting is for a sufficiently large P, this is still a contraction. Okay, so the P norm, we all know that infinity norm can be approximated by the P norm. As you make P larger and larger. So for a sufficiently large P, you won't get the same gamma, you get a slightly different gamma here. Okay. What would be something like P power 1 over the dimension of this or something like that. So anyway, so the idea is that you can, even though it's an infinity norm contraction, it's also a P norm contraction for a sufficiently large P. Because the difference between the infinity norm and the P norm would be something like P power 1 over P or something like that. 1 over P. Yeah.
So here the state is being generated by some offline policy.
Yeah.
Now, if you like, so then this T operator seems to be different than the Bellman operator because there you take the action A tilde and you go to the corresponding state.
I don't need to. I'm just here. I'm just trying to learn the optimal policy. I'm trying to learn the. I'm just giving it. I'm given a trajectory. So you've taken your car whatever policy you use, your autonomous driving vehicle, driven it through the city, and then you want to figure out what the optimal policy is. So I don't know what the optimal policy is. I only have a trace from a specific policy that I'm using. Despite that, you can find the Q function from you can find the optimal Q function. Once you find the optimal Q function, like when I mentioned, then you just have, if I figure out Q, then I just can figure out the optimal policy for later purposes. I just need to figure out the true Q. Here I'm trying to learn the true Q, Q star, from a trace from a given policy pi. Okay, I'm not implementing this policy to obtain the trace. I'm just given some trace, like data-driven decision process is the name of the bootcamp, right? So you're just given some data. From that, I want to learn the optimal policy. You can also try to implement it online. To some extent, I think Sean's talk will be somewhat like that, where you run an episode and then do it again and do it again, and then you're learning from the policy that you're generating along the path. But that's not what I'm doing here. Here, I'm just given one single trace, and from that, I'm trying to learn something.
Oh, is T still not a contraction under D pi star even, right?
No. Yeah, so this is true. So the Lyapunov function that we use in this case is this. Okay, so it's not the 2 norm, but the P norm.
This statement about the optimal delta operator being a contraction is sufficiently large P, is that true for all infinity norm contractions, or is it like specific?
Any finite dimensional infinity norm contraction. If it's not finite dimensional, then it won't be. I mean, if the proof is so if you plus this less than or equal to if this dimension is D, then this is greater than or equal to right? So if I do 1 over P, okay, close to 1. Yes. So if it's a contraction in this norm, it will also be a contraction in this norm because you get to multiply it by D raised to the power of 1 over P. For sufficiently large P, that will be small enough. That will be close to 1. Of course, it's all finite dimensions. So this is the more natural function to use instead of comparing QK and Q star in the 2 norm. It's better to compare QK and Q star in the P norm. But if you remember, this morning we did this. But also the other problem with using the infinity norm is not differentiable. So that's another issue. Not to go further. So this morning we did this, but I can't do this anymore because this is not a quadratic. So when I take the second derivative, the Hessian is no longer the identity, right? So you need some other trick. So this is a well-known trick to optimization theorists. It turns out the P norm has something called the half of the P norm squared has something called the P minus 1 smoothness property. So what it means is that this is it's very straightforward to prove this, but it's an interesting property. So you can still act as though you're doing a second order Taylor series. So the only thing that matters here is less than or equal to. It doesn't matter if it's equal to or not. This morning it was equal to. So now I have a less than or equal to. But everything else works. Okay, so you can just essentially go through the identical analysis that we did this morning. And
So the factor P shows up somewhere in the result.
yes, the factor P will show up from that result. Actually, my postdoc Mehrdad is typing all of this. So I don't know if it's useful. I can put it on the website. Yeah. So we can show you what exactly. Yeah. Any other questions? Okay. So the rest of what I'm going to talk about, everything is pretty much open. So I'm going to tell you what is currently known.
Quick question.
Yeah.
In this P-norm, the projection is no longer a contraction, right? So you have to worry about.
I'm not, so that I'm going to talk about that now. So this is for the tabular Q line. Yeah, as I said, everything else beyond this is there's a lot of open issues here. I'm going to talk about them. Yeah. Okay. So Q learning. Linear functional approximation. Okay. So the most natural thing to do is assume that the optimal Q function is also linear, like Q pi, and then you do this. So this is the natural extension of TD learning to Q learning with functional approximation. Okay. But this is known not to converge. Okay, so there is a famous example by Baird, which I don't remember, has lots of states and so on. So in general, it doesn't converge, and you can try to do simulations also, it doesn't converge in general. Okay. So what to do about this is still, I would say, somewhat open. So what I'm going to mention today is an idea due to Remy Munoz, Pasvari, from around 2008 or 2009, but it's more concretely written recently in terms of finite time bounds and so on by Zaiwei Chen. It's now actually Adam's postdoc. This was part of his PhD thesis. Maybe 2022. Very recently, we're putting on it.
Question.
Yeah.
So do you have some intuition for why it doesn't converge?
Basically, it's the mismatch of the norms. Mathematically, at least, why you can't prove convergence. I don't remember how the counter example works. It's a somewhat involved counter example. But basically, so there is a projection norm here, which is so before I avoided in the last, when you have tabular in the tabular setting, everything was I use the P norm throughout. Here you cannot, because here the projection, when you're basically trying to project the Q function onto the space of phi, you're using the natural norm that comes up is the 2 norm. And this is not compatible with the P norm or the infinity norm. And so this norm mismatch basically makes the convergence proofs not work out. But that's not a good answer, because that doesn't tell you why the counter example works. But I think the counter example, you have to go look at Baird's example. That's like 8 or 9 states, and it's complicated. But proof-wise, why it doesn't work is that there are multiple norms involved, and we were able to solve it in the tabular case. But in this case, the norms don't match, and so you can't get contraction results very easily. So when you multiply the P norm by the 2 norm and then together, now it's no longer so before it had this property, the projection phi T pi dot is a contraction mapping because this is a contraction in the d pi norm, and this is a non-expansive in the d pi norm. Now, this is a contraction in the infinity norm, and this is still a projection in some 2 norm. And these two are not compatible.
So the counterexample is set up so that
I don't know if the counterexample was set up like that. I think the counterexample probably preceded all of these kind of proofs, but I don't know how. I can't remember the details of that. It's a very old example. Yeah, but at least I know from a proof perspective, it doesn't work because of this incompatibility. So what works reasonably well, but still, I think there are probably lots of dependence on this d-min kind of things in the finite time results. So I think there's probably something worth looking at here. Is that actually people do this in practice, and I don't think anybody understood why they're doing this in practice, but I think I understood it by reading the Chen-Clark methodology paper, but I think the original idea was already in the Munoz Chipaswara paper. So weirdly enough, what you should do is fix a theta here only. So there are 2 thetas here. One of them is fixed. Okay, you fix it, and then run the algorithm for t time steps. Okay, so let's say t time steps. Run it for t time steps, and then swap the current value of theta k with theta bar. So it's like a 2 time scale algorithm. So the bootstrapping that you were talking about, you don't bootstrap, you just fix it. So it's a combination of bootstrapping and this one-step gradient descent. All of this messes up the convergence proofs. It turns out that if you do this, then you're just learning some arbitrary thing here, and then you show that slowly somehow over time. It's a very slow convergence if you do it this way. In practice, people, I don't know whether they wait this many time steps as in these papers suggest. And one more thing in practice is, of course, you are not doing this, you're using a neural network. So what they do is that they use what is called a target neural network, whose weights are frozen for a certain amount of time. And then you try to learn the parameters of another neural network using this. So think of this as the parameters of a neural network. You fix one neural network, learn the parameters of the other neural network, take the parameters of the other neural network and swap it out with the first neural network's parameters, and then again do this. So this is we prove to converge.
Did you omit the discount factor?
Sorry,
So you are omitting the discount factor, the gamma?
No, not I just.
So you're just saying run fix theta hat and then run it for t steps.
Yeah, some t steps, and then swap, change theta hat to theta k, and run it again for 3 more steps, and a few more tricks.
But the main difference being earlier you were changing it every step, now you're batching.
Plus other tricks. I don't remember what other tricks are. There's some truncation that's needed, some projection that's needed, but those all seem to be for proof reasons. Because this seems to be more fundamental because of this bootstrapping issue. You're constantly trying to change what you're trying to seek here, and that's what makes the problem difficult. The one step of gradient descent doesn't make complete sense, right? Because you're changing the optimization objective each time. Here, you're not doing that. Yeah.
So does it make sense to think of this, within each batch, sort of as solving a different fixed point problem with respect to this theta bar?
Exactly. Yeah, that's exactly. So you're trying to learn something fixed here, you're trying to find this to match R minus something fixed, no longer the original fixed point. But it's not even a fixed point equation because this is not equal to this anymore. We're not trying to set this equal to this. You're trying to set that equal to this in some very slow time scale. So you're trying to set this equal to this, but here it's no longer has theta k, so it's no longer has a fixed point kind of interpretation. Just some equation you're trying to solve. So
It's a convex minimization, actually.
yeah, convex minimization, I guess. Yeah, because you can just think of this minus this square. Yeah, right. Without bootstrapping, basically. Yeah.
Oh, a quick question. So maybe it doesn't work in practice, but theoretically, if it's just one step of gradient descent, let's say you did one step of mirror descent or something like that, that's like compatible with the P norm, does everything check out?
Not that I know of, I'm going to talk about mirror descent in a second. Okay, in a slightly different context. Yeah. And I don't know if there's a compatible Bregman divergence for which this will work. It's an interesting question. I don't know. Good question. Yeah.
What is big T?
What is what?
How do you choose?
Oh, yeah. So when you do finite time bounds, the bounds will depend on T, blah, blah, blah.
I see. So it's a parameter.
Yeah, it's a parameter.
Okay.
Yeah. Choose it to make your errors. Okay.
So it could be that for fixed big P, there's still a counterexample if we run it for it. So suppose someone fixed the path size and ran this, it actually wanted
That's a good question. It might be. It might be. But so it might depend on the problem, what the T is. Yeah. That's what I mean. So I don't think these results are, I would say that I liked it a lot, but I think there's probably still a lot more work to be done here. Yeah. I think there are a lot of problem dependent parameters in the error bars. Yeah. Okay, so Q learning can be thought of as an alternative to value iteration. Value iteration tries to solve Q equals TQ, right? Instead, what Q learning and TD learning, all of these things do is that they look at the difference Q minus TQ for approximate TQ, because we don't know the probability transition matrix, then adapt whatever parameters you're trying to learn by looking at this difference, right? This temporal difference. An entirely different set of algorithms can be obtained from policy iteration. Okay, so fix a policy pi, compute Q pi. So let me call it pi k. Okay, fix a policy pi k, get the Q function associated with that policy pi k. How would you do it? Using TD. We already know how to do this, right? Now you have a new policy. Okay, so now you can obtain a new policy by doing R A Q pi. You get a new policy. This is what Wayne mentioned this morning. So this is policy iteration back and forth. Right? But the problem with this is that this will not work in the setting where you don't know the probability transition matrices, because the optimal policy here could be deterministic. So for each action, for each state, you might take a particular action. Whereas to learn the true Q function, to be able to do this, you need to be able to visit all state action pairs. So what you do in a reinforcement learning setup is still do the first steps. Fix a pi k, learn Q pi k with the without function approximation using TD learning. And then your new policy, pi k plus 1, is a softer version of this policy. What do I mean by that? So beta goes to infinity. then you're automatically finding the maximum, right? So this is just the soft max version of true maximum. Everybody understand this? So the larger the beta is, you put all your weight on the action that maximizes Q pi SA. Okay. So this is a reinforcement learning version of policy iteration. And actually, this is called natural policy gradient. So nothing about gradient descent here, but
It's a regularized leader kind of thing.
yeah, it is actually, this turns out to be policy gradient. Actually, it is like gradient descent with
Negative
mirror descent kind of thing with the KL penalty. If you do that, and then if you can just cleanly write it in this form, people might have seen this in lots of other contexts, this kind of thing. So it's called natural policy gradient because it's derived from a policy gradient, from a gradient descent perspective, which with the appropriate Bregman divergence. But after all that, you can clean it up and write it in this form. Okay. So the only thing I'm going to mention here is that there are lots of interest in this. Is a very, very current area of research. There's been a lot of work in the last couple of years. There's a very nice long paper, 60-70 page paper by some can remember for sure. It's a 2020 paper exploring gradient descent type of algorithms for finding optimal policies. But the results they provide are not for the last iterate. So what they do is somewhere along the path, they say that you will find you'll be very close to an optimal solution, which may be okay in some optimization contexts, but not so great for reinforcement learning context. There is a recent paper by Wei Chen and Madhuri again, which actually gives you last iterate bounds, except that it has this d min that I mentioned in the morning here. So even though it's function approximation, but you're really somehow there's a dependence on the state action pair to the bounds, which is not desirable. So I think there's some interesting work to be done here. The main thing I want to mention here is, okay, so we now know for fix a policy pi, we know how to learn Q pi through function approximation. But how do you make sure that this whole thing converges where a daily pi k is in this? So I'm just going to, I know I have 15 minutes, but I'm going to wrap it up. And we can have some questions if you want. The Lyapunov function that one uses in this case. Okay, so what I'm saying is that let's say Q pi k is found exactly. Okay, not using TD. Let's say somehow you're able to find Q pi k exactly. Then I want to show you what Lyapunov function is used to show the convergence of this whole thing. Okay. But in reality, to get proper finite time analysis, you also have to incorporate the TD analysis that we've been talking about all day. Okay, so you have to incorporate, use this Lyapunov function for the outer loop, and then a different Lyapunov function for the inner loop, and together we can get finite time. Okay, so what is a Lyapunov function here? It's a very nice Lyapunov function. This is in this other wallpaper. So it's a weighted KL distance. So for each state, there is a policy, right? There's a randomized policy for each state which uses the action. So let's say pi star is the optimal policy or any policy, it doesn't matter. Let's say it's the optimal policy. So this is the KL distance between the optimal policy and your policy. Okay, and it's weighted by something which I call d tilde pi star west, which is what's called the state visitation probability. Of state S and that policy pi star the optimal policy. The state visitation probability is a very interesting Let's multiply by 1 minus gamma for it to be probability. So what it is look at the probability of being in state. So mu is some initial condition. Okay, so you're starting the system, let's say, with some initial distribution. Okay, the state visualization probability is just basically the probability of being in state as summed over time, but multiplied with solution. So multiplied by gamma power t, but of course, this whole thing, when you multiply, you have to multiply by 1 minus gamma for it to be a number between 0 and 1, right? So this is what the state visualization probability is. Okay. And so it's a very nice Lyapunov function that they use to show that. So this shows that this iteration is stable, but as I said, this cannot be evaluated exactly. So you have to use function approximation or something to evaluate this. So we have to use analysis that we did this morning and early this afternoon, along with this Lyapunov function to get that performance graph as well. Yes.
So is it possible to get like single step analysis in this? So like you take one step of the gradient or some steps of the gradient descent for the TD for the first part of it, but not do it until convergence.
Sorry, say that again. I don't quite understand.
So there are two steps in this.
Yeah, there are 2 steps here. Yes.
It's like alternating minimization thing. So the first step you are
No, it's not alternating. So what this will involve. So you fix a policy pi k, and you have to run an algorithm for a while here to get the q pi k estimate.
I guess the question is, suppose you terminate the policy evaluation in the middle before it's convergent.
Oh yeah, that's right. So the answer will be in terms of how when you terminate that. That's correct. So so this part has 2 errors. One is if you don't run it to infinity, there's an error, and there is an error due to function approximation, right? So it will be sum of those 2 errors, and that will accumulate, and you have to figure out a good way to control all of that. So that's all in this paper. So there is an issue because if you do this, then it's possible that pi k of a given s can get closer and closer to 0 for some actions. So you can't do that, and so they do some other trick to this is still an open area. I just wanted to give the high level outline. So there are 2 things that are very well known. One is why this converges if you know q pi. I know how q pi can be estimated, and I can give you error bars. Putting those together is an interesting problem, and there are multiple results along those lines, but I think there's more to be done. Yeah.
So when this converges, would it converge to the optimal?
Right. Yeah. So you can show that. Yeah. It can. So. Okay. So that's an interesting question. Does it converge to the optimal pi? What I can show is that the value function associated with pi k will be better than the value function associated with any other pi as k goes to infinity. The problem with this is that the optimal policy may be deterministic, and this is a randomized policy. So it will eventually go to the optimal policy, but I think there is some you have to worry about the KL divergence being properly defined out on the spaces and all that. But you can show that compared to any other policy, I'll eventually do better. Yeah.
For a linear approximation, do we have a similar projection?
Yes. So yeah. So exactly. So this paper uses the linear approximation part here, and this here, and together they show convergence. But they also handle the fact that some of these actions might have very close to 0 probabilities, and so you're not exploring the state space very well. So what they actually do is that they use a fixed policy. Kind of interesting. They use a fixed policy. Running out of symbols, let me call it pi hat. Yeah, and they evaluate any other policy pi k using this fixed policy. What does this mean? So you have to do a multiply by some sort of an importance sampling ratio to convert from the performance of this policy to the performance of this policy, and that adds additional variance. And so you get a additional nasty variance term because of that. So these are all interesting things to understand whether there's a way to get around it. So likelihood ratio for us before. So basically multiply by likelihood ratio at each time instant to basically convert from the performance of one policy to another policy. Okay, so that's it. That's all I have. No questions. Yeah, no.
So do you have a sense of like under what conditions you'd want to do this policy iteration variant versus like the value iteration variant? Like one converge faster than the other?
I don't. Okay. It's a very good question. As I said, both of them seem to have stability issues in the sense that, as I said, when you do Q-learning, you have to use this thing called a target, and the basic vanilla version of Q-learning does not work. And so people use, in practice, all of these algorithms require a lot of tunings from what I understand. And so some people believe that policy iteration is more robust. I don't know. I mean, Shyam Kakare had a conversation on Twitter and he said it was more robust, but I don't know exactly in what sense. But it's an interesting question. So I think that it's like, so historically policy iteration, when I was in grad school, I was told that it converges in a finite number of steps. But of course, each step would take a very, very long time to evaluate the policy, right? So I don't know. So that both have their own advantages and disadvantages. I think the one thing though is that I guess value iteration relies on the contraction property. So if gamma is close to 1, I don't know if it will slow down compared to policy iteration. I'm not sure. These are all open questions. I mean, if anybody can answer them, I think that'll be good.
About a linear Q function, is there some natural way, like, so you're going to reach a certain floor beyond which you're not going to have any projection? Is there a natural way to add more covariates at that point? Someone use this analysis to figure out what direction, what else you need to add to actually.
I see. I mean, I guess in practice, people use neural networks. Nobody uses linear function approximation. And neural networks are pretty expressive, but you don't have to worry about this kind of thing. Now, there's an interesting question: what happens if the state space is very, very large, or infinite, actually? So then there's a question of stability. The system may not even be stable. So if you use a policy that's not stable, then you won't be able to actually evaluate its value function. Well, value function is infinity. So what do you do? So as you're running through this algorithm, if at some point you reach a unstable policy, what do you do? This is something, I think there's a paper by Devabrath and Shaman, I don't know if Shaman's here, that sort of addressed this question. So I haven't looked at it carefully, but that's an interesting question. What to do with infinite state spaces, which occurs in a lot of examples. Now, in the special case of LQ problems, there is so you can parameterize it within the class of linear. Because you know the policy is linear, and so there's this work by Merriam Fazal and others, where they prove that if you do policy iteration within the class of linear policies, you have convergence. And it's actually been extended to even etching controllers by Bashar and Kaichin Zhang. But not in the, it's all in the case where you observe the state exactly. Traditional etching they also allowed for imperfect state observation, and I don't think that's been studied here. But that becomes a POM DP. So
one other thought I had, the discussion in the morning, we always think of gamma as fixed. But you kind of know that for smaller values of gamma, your convergence for the TD set is possible. You know any algorithm which tries to adjust it, change the gamma?
Yeah, I don't know. There's a paper by Nan Jiang, my colleague, that did this when he was a PhD. I remember him talking about it during his job talk at Illinois. He argues, there's a paper by him where he argues, actually, if you're interested in gamma equals 0.98, he said during training, you should choose gamma equal to 0.9 or 0.8. And this actually has better generalization capabilities than actually using the true gamma. But that was, if I remember correctly, it was for a structured setup. I think like somebody asked one morning, where he's trying to learn the probability transition matrix and then learn the policy from there. But but in his talk, I remember he said that in practice, people always use a smaller gamma for convergence reasons, and then deploy it for even larger gammas. But I don't know if there's a systematic study that is done apparently. Anything else? Okay, well, thank you.
Have a great